Good morning, everyone. Welcome to Julia EO conference. It's great to see so many technocrats, leaders, and change makers gathered in one place today. This conference is about learning from real experiences, meaningful conversations, and insights that help us grow in business and in life. To begin today's session, it's my pleasure to introduce our first speaker, Amit Ruhela. Dr. Amit Ruhela, the HPC Group, joined HPC Group at TACC in January 2020. Before TACC, he was working in the network-based computing laboratory at the Ohio State University. He has more than 17 years of R&D experience in HPC, social computing, and telecommunication. He is currently working on novel designs and algorithms in parallel communication to deliver the best performance and scalability for scientific and engineering applications. He has also conducted large scalability studies and performance evaluation of HPC applications on leading supercomputers. Dr. Ruhela received his PhD degree from IIT Delhi and BTech degree from NIT Kurukshetra, both in computer science. He has worked closely with researchers from the Ohio State University, NICTA Australia, IIT C. Delhi. He has also worked with computational scientists and researchers from TACC, SDSC, OSC, UMH, LLNS, University of Oregon, NCAR, EPFL on NSF and XSEDE proposals. So I would like to welcome Amit Ruhela.
Thank you for the introduction. My name is Amit Ruhela and I'm a research associate and manager at TACC, Texas Advanced Computing Center in Austin, Texas. And today I'm going to present our benchmarking for TACC systems as well as my experiences with Julia so far. This presentation is basically three parts. First, I would say about the systems that we have at TACC. And second, we'll look at the benchmarking methodology that we are going to use or we'll be using in our upcoming systems. And third, some of my experiences with Julia. So regarding TACC, TACC is a small center. It's almost like 200 employees working at TACC, basically on high performance computing systems. And we deliver some of the nation's large scale HPC centers. TACC is young. It's like 25 years old. We started in 2001, 190 staffs, including 70 PhDs. We operate some of the largest systems like Frontera, which is going to expire this year, but still the largest in US academia. Then we have Stampede 3, Lone Star 6, Vista, Jetstream, and Chameleon. In total, we have 12,000 nodes, 1 million cores, 1,000 GPUs. And we support around 3,000 projects for 40,000 users every year. These are our systems as of now. The latest system is the Vista machine, which is AI-centric machine. And we have a continuous need to build the newer systems. Particularly, the demand comes from the changing hardware architectures, the new workload requirements. For example, AI is at boom now. Everyone wants to do AI whether they know it or not. And then newer workloads are requesting newer type of systems that can deliver the performance they need. These are the systems, some summary of those systems. TACC was primarily the Intel systems, for example, Frontera and Stampede 3, both were large-scale Intel systems, but the shift has moved to AI, and for AI, we have now set up the Vista machine, which is Grace nodes and Grace Hopper nodes. Grace is delivered last year. It has 827 nodes with 576 GPUs. And now we are moving towards the horizon. So we are moving from Intel to NVIDIA platform. So Horizon will be delivered this year. Some part of the system, at least the Grace Blackwell nodes will be delivered this year, and Vera nodes, which is the CPU systems, will be delivered the next year. So Horizon machine will have 6,000 nodes, 6,752 nodes. The GPU would be NVB200, and we would have 4,000 GPUs. The interconnect for this machine would have a NDR interconnect for CPUs and XDR for GPUs. So before delivering Horizon, we just gave Vista to the nation, and this is a AI machine centric resource, mostly funded by the NSF, and some part is delivered or funded by the UT Austin AI initiatives. It's a bridge to Horizon. People are moving from one domain to another. It's first in the sense of it's our first ARM system and first NVIDIA systems that deliver both CPUs and GPUs. And this machine has 256 Grace nodes. Each CPU has 72 cores. It's a dual CPU node, which means 144 cores. And it delivers 7.1 teraflops of floating point 64 performance. We have a 600 Grace nodes, Grace Hopper nodes, which are basically H100 nodes, and each Grace node have 240 gigabytes of low power DDR5 memory, whereas Grace Hopper contain 120 gigabyte of memory as well as 96 GB of HBM3. So in terms of OS, it's powered by Rocky 9.3 and is connected by the 15 petabytes of vast storage file systems. So looking at the Grace super chip, it's a super chip containing two Grace dies, and each of the chip is connected by the NVLink chip-to-chip 900 Gbps connection. Each chip is connected with the low power memory, and it can deliver 1 terabyte of memory bandwidth for the two CPU subsystems. That's a diagram for Grace Hopper, where there is one Grace CPU and connected with the Grace Hopper GPUs via the NVLink. And for the TACC systems, we have 120 gigabyte of LPDDR5 memory and 96 GB of GPU memory. Looking at the architecture of TACC Vista machine, on the top we have a core switches, 16 core switches, each connected with the CPU systems and the GPU subsystem. So in a rack of CPU systems, we have 64 nodes connected via 800 Gbps dual line. It's basically 400 Gbps line. We have a dual line because we don't have any interconnect so far which can deliver 800 Gbps of speed. So each of the top rack shelf switch is connected with the core switches via 800 Gbps, and 64 nodes are there. And this is a 4 racks of CPU systems, and then 19 racks of GPU subsystems. And these subsystems are connected to the storage network via a management switch. So we are now establishing the Horizon machine. TACC doesn't have a space, so we are moving to the Dell campus in Round Rock, Austin, Texas. And the data center is developed by SEBI, and the center has been developed. Now we are installing the racks, and we are also installing the various other system things. So Frontera was 600 megawatt, but Horizon is now moving to 13 megawatt as of now. We started with 9, but with the discussions with Dell, Nvidia, and other vendors, the energy consumption has increased to currently it's now 13 megawatts of data center. So in total, we will be having 8,368 CPU compute nodes, and this is not correct. Oh, that was the Frontera. But now these are the current pictures which we have taken in September, where the cooling was underground cooling was installed, and then now we have the floor ready. We are getting the racks from Dell as of now, and we will be installing the Blackwell nodes or Grace Blackwell nodes soon. So each rack in the Horizon system will be having It's not NVL 72. We don't need to have 72 GPUs per rack. We can have even lower. We can go just with the NVL 4, where 4 GPUs could be in the one node. And then Horizon GPU racks will have 144 GPUs, and will be around, like, each rack would be 15 kilowatts per rack. Whereas the CPU systems will roughly have the same 72 dual socket nodes. The rack power would be 100 kilowatts per rack, and so we will be having 28 GPU racks, 66 CPU racks, in total 128 cabinets for this Horizon machine, consuming 13 megawatt of energy. Now I'll go to the second part of my presentations, how we do the benchmarking for these machines. So when we started with the Frontera, there was a basic set of benchmarks like MPI, IO, Stream, HPL, and some other key applications. And at that point of time, we had a goal of getting that 2 to 3 times performance improvements against the Blue Water system. So those benchmarks were defined in 2006. Most of them are still relevant but do not scale. Some of them have become obsolete, and we definitely need a newer way of benchmarking the newer machines. Those were the tests that were done for the Frontera machine. Out of, like, most of the machines, most of the benchmarks were able to give over 2 to 3 times of performance improvement. In total, we get 4.3 at the time of Frontera system. But now we have defined the characteristic scientific applications for benchmarking the newer Horizon machine, and the goal is to find the applications, the actual code, which are basically represent scientific code or workflows. Those are the codes which cannot be solved today, which will require a newer machine, and we need to define a figure of merit. How can we compare the benchmarking performance from the previous machine to the newer machine? And therefore, our goal is to basically get 10 times performance improvement over Frontera. And this is not an easy way of figuring out the figure of merit. And in this figure of merit, we have defined four characteristics. Does the runtime change? Does the runtime change from the previous machine to the newer machine? Can we run it? Can we run it faster? Basically, the strong scaling. Can we keep the problems? Can we change the problem size? Can we run the bigger problems within the same time frame, which is basically weak scaling? Can we use the lesser of the system, or high, like fewer nodes of the system compared to the previous system, which is basically a throughput? How many instances of the same application can we run over the newer machine? And does the physics change? Can we add more physics? Can we add more dimensions or variables for the same application and run more use cases within the same run? So the performance is multiple of all these four factors, basically the time, size of the problem, ensemble, and physics. So in 2021, we started with an open call for all the scientific applications in the United States, and we got 140 applications for evaluation for the newer machine. Right now, we have 20 set of these applications, which we have worked together with the developers and identified. These are the 20 applications which can scale or can prove the performance for over the newer machines. Some of these domains are astronomy, astrophysics, biophysics, CFDs, geodynamics, material science, and others. So in the last 2 or 3 years, we have worked with the developers. I worked with NAMD developers. I worked with PSDNS developers, and we have really run the large test scales over the Vista machine, and we have predicted what kind of performance can we get over a newer machine. So some of these applications, down-selected applications, are AWP Odyssey, Athena K, Changa, Milk, NAMD, PSDNS, CSOL, Vespa, EPW, NGO, and MUST. And these applications have been, these are the projections that we estimate as of now. For example, Earth application, AWP Odyssey by Yifeng from San Diego Supercomputing Center, it's projected to have 11.5 performance improvement than the previous Frontera machine. Astrophysics, Athena K by Jamestown, it's projected to have 22 times performance improvement. Changa by Tom Quinn, Physics, Milk, which is a lattice QCD for flavor physics. NAMD, which I worked with UIUC developers, it would have at least 10 times performance improvement than PSDNS by PK Yang from Georgia Tech. CSOL is by Alice Gabriel from UCSD, 6.3 performance over CPU systems and 2.4 times over GPU systems. So these are the applications which we have seen so far. This EPW is weird in the sense like we think it will give 2400 performance improvement. The reason is once we move from CPU to GPU core, the performance really, like, there was no GPU component for that application before when we ran it on Frontera, but now on GPU they perform really, really good. This is exception. We are going to remove these exceptional cases. We don't want to take our factor 10 times to like impacted by 2400 times performance improvement by EPW. So definitely this will be out of the key applications for benchmarking. Let's take a look at some of the performance results that we have run so far with the Julia on our systems. We are relatively new for Julia. We have installed 1.12.3. I think that's the latest version for Julia, and these are some of the performance numbers which we have measured so far. My background is MPI, message passing interface, which is a communication library for communication between the nodes, and these are some of the benchmarks which we have run. And this is the benchmark OSU micro benchmark, which is developed by DK Panda and his group in Ohio State. And what it does is it sends a message from one node to another node and measure the latency. How much latency do you expect while using MPI communication? This benchmark measures or compares the performance of OpenMPI 5.0.a against Julia 1.12.3. And Julia does, so in this experiment, I'm not using the benchmark which are part of the Julia suite, but it's I'm not using the OpenMPI, which is part of Julia suite. I'm using the OpenMPI, which is the system MPI, and I have configured my Julia in a way that it uses system MPI. And this shows the performance between Julia wrappers as well as the OpenMPI when they build the OSU benchmarks. It's almost the same. There is no impact of wrappers over the system MPI, and the trend is same for all the kind of message size starting from 1 byte to 4 megabyte. However, the bandwidth, we see some differences in the bandwidth benchmarks, and we see that Julia wrappers perform little worse than OpenMPI. I don't know the reason. It might be some tuning issues, or it might be something else which I need to investigate further, but in a sense, both of the MPIs are able to, both of the implementations are able to saturate the network bandwidth, which is 50,000 megabytes per second. The interconnect is 400 Gbps, and so both of them were able to almost saturate, but with some differences, which is good. Then we have a collective benchmarks. Those were the point-to-point. This is a collective benchmarks, and each benchmark is run with 144. This was run on CPU cores, so 144 cores per node, and this is the kind of communication which we see. Again, Julia performs pretty well for collective benchmark. Basically, the broadcast, which basically sends one message to all other ranks over the two nodes. So definitely Julia makes much better communication for the broadcast communication. And this is the reduce case. In this case, I do the reverse. I do see the reverse pattern where at least Julia performs. So this is the line for Julia, which higher is like worse because it's a latency, and OpenMPI does pretty well with the small and large message size, and there is a weird 128 byte message size where Julia abruptly shows higher latency. We need to investigate. This could be a system issue or tuning issue. Most of the time, whenever these benchmark or communication libraries are written or delivered over the general public user space, they are not tuned for a particular system. So some tuning is required always to get to avoid these kind of abrupt latency latency issues. In terms of all-to-all communication, which is more dense communication, we do see both Julia and OpenMPI works pretty well or close to each other. This is this trend is persist for both the small and large message sizes. Last, I ran some of the scaling performance from 1 to 32 nodes of Grace Hopper system, and I measured the all-to-all scaling performance. In this example, I chose the message size as 64 bytes, and each node has 144 cores, which means I'm running this benchmark over 144 ranks to 4,608 ranks from 1 to 32 nodes. And as you can see, as we increase the number of nodes, since it's a dense communication all-to-all, which means O(n) square communication, so doubling the nodes should impact 4 times the latency. And I do see those kind of like 4 to 5, almost like four times performance degrade over 1 to 8 or 1 to 16, but from 16 to 32 it's 1.5 times, not the 4 times performance degradation. But this is expected, and this shows that benchmarks run without any issues on our system. So last, I just want to make some concluding remarks for the experiences that we have on our system. So while using the Julia, there was like seamless installation. There was not even a single issue. Just download, extract, and set up the LD library path and use the Julia. There definitely with the benchmarking which we have run so far, there are some tuning issues which we need to identify, set up the environment variable correctly so that every user can get the same kind of performance or a tuned performance. Our systems are uses the shared setup. We don't want every users to install their own or create their own Julia setup. We provide the Julia module for users, which would have most of the libraries. So we need to identify how do we maintain those versions, how do we maintain for CPU and GPU libraries which are part of the packages installed within the Julia. So this is a question to me because I'm a system provider and I provide the Julia to our users. So I need to find out what is the best way, what other centers are doing across the world for Julia, for providing Julia to their users. We have been doing the training for our users. I did one training session last year to our users where I make them learn Julia. And though it's a relatively new but much powerful, I feel it's much better than the Python in the sense that it is a single binary. So when you install Python, it's tons of files or millions of files, and each files, when anyone accesses the Python, they generate so much load on the shared file systems. And at least in the case of Julia, that's not the case. It's a single binary, and it's much more file system friendly. Last, I would like to see from some of you are Julia developers or part of the community, so I would like to see some kind of benchmarks, just like ML Commons. If you have ever used ML Commons benchmark, they have a work groups, and under work groups there are benchmarks. So those benchmarks are used by all the researchers in entire world for AI benchmarking. Do we have such kind of repository, or do we have such kind of mini apps that users can use from the Julia setup? And can you use those benchmarks for large scale performance evaluations or small scale or whatever, the system benchmarking and other performance runs. So I would like to definitely talk with the people sitting here for the benchmarking source, or can we come up with such a work group which is basically a Julia work group for performance benchmarking over the HPC systems. So that's all from my side. Thanks for attending. If you have any questions, I would be happy to take. Thank you. Yeah.
So I'm very impressed from the numbers you achieved with optimizations of the code. I was saying that I'm very impressed from the performance optimization that you achieved. It's like 22 times, 11 times is like a very good optimization.
Yeah.
Is it because of the work that you did on the code, or is it because you're using a different hardware or more resources?
Hardware is one factor which basically gave you performance improvement, but we have been working with those developers for last 2 years. So we are constantly defining newer ways, like for example, NAMD. I will give you an example of NAMD. So we have got almost 10 times performance improvement hardware wise. If you just compare hardware to hardware, it may be 2 or 3 times performance improvement.
Okay.
But what we have done so far is running the entire code which was running on CPU to GPUs, and from GPU,
Okay.
like NAMD runs in 2 mode, offload and resident. Like offload when you can offload some part of the computations to GPU, but resident is like when most of the components goes to the GPU and there is less CPU GPU communication.
So there is some CPU
So
to GPU here.
leveraging the
between
new
times.
GPUs, definitely hardware improvements, memory bandwidth, number of cores, all these factors accumulate, and then we resolve the bugs as well with like performance bugs. So,
Okay, thank you.
Yep.
Thanks for this great talk. I was wondering when you compared OpenAPI with Julia. So I guess the basic OpenAPI implementation was the same, but once was a C program maybe against or C++, I don't know, against Julia program. Did you had a look at the garbage collector? If this was some issue, maybe did Julia collect allocate some memory, which was not the case for the C program. So maybe this could be some explanation why there is so much difference. Because as far as I know, there should be no intermediate memory allocation when you hand off the things to the MPI library. So maybe that could be one way to check if there is some garbage collector issue.
I would take a look. I don't know about those things. I feel the underlying MPI is the same. When you call benchmark with OpenMPI, and when you call it with Julia is just a wrapper. It's not even like it's a wrapper around the underlying MPI. So it's using the same MPI in both the cases. So garbage collector, this should not be a case as I feel as of now, because each benchmark is run thousands of time, and every time before the arrays are erased so that the new data comes in. But I will take a look. I don't have any clue about the garbage collection for the Julia. Should I define it?
Might ask a second question? So I'm really fascinated by the by the way that you showed the procurement of the cluster. So there's a lot of things that you can tune, like do I spend more budget on the GPUs or more on the interconnect or more on the disk speed? So how do you reach to this how do you decide how to spend the funds wisely on to have a good compromise between performance,
CPU and GPU?
CPU, GPU, disk, and all this?
So your question is, we were having CPU systems and now we are adding GPU systems. How do we add the newer GPU system? How much?
Or just how do you decide where to allocate more funds? Is it better to have better GPUs or better CPUs or more better interconnect speed?
So I have been at TACC for last 4 years, and every year we have a user group meetings where we ask users like what kind of code they are running, how GPU ready they are. For the last 3 years, none of them say that they need a GPU or they need a very large amount of GPU. TACC provide resources to thousands of applications, and most of the applications, like 98%, above 90%, most of them are not GPU ready. Except if you just leave the AI applications, most of the applications are still trying to adopt GPUs. And that is the reason we are conducting hackathons every year now, for users to come to TACC, work with NVIDIA, work with us, looking at their code, what part can be offloaded to GPUs, and slowly try to run computations in a GPU way. So from the last year and from the AI initiatives by the government and many other UT Austin initiatives, we thought there is a need for now GPU systems, and we allocated part of the system for the GPU. And this is apart from that, our responsibility doesn't just tie to the GPUs. We also have the CPU systems like 4000 CPU nodes as well for the applications that haven't or they don't need to go to the GPUs. Some of the applications have really scaled well, but most of the applications still needs to adopt the GPU. It's not easy. I think we need to provide resources to both, and it's about the money that we get, like 400 million for setting up this new machine, and we just did like some kind of 60-40 allocations to the CPU and GPU.
Thanks.
Any other question? Okay, thank you.